pitting corrosion is the next type of important corrosion because it is seen in oil and gas industry to a very large extent. It is especially seen in those components which have an oxide film on the top. So the most common material to undergo pitting corrosion is stainless steel. The other alloys such as nickel or chromium alloys will also undergo pitting. Carbon steel will also undergo pitting in highly alkaline environments, but I'll come to that in a bit. Now, if we take the example of just a simple pit, let's start with the carbon steel. You have the carbon steel and it has been exposed to chloride and water and oxygen, of course. So in this case, the corrosion starts normally, so in the form of uniform corrosion. It has developed a lot of corrosion products on the top. Now, the corrosion products mean that some area of that material is now completely covered with corrosion products and the ingress of chloride is reduced. In the other parts, however, the chloride can still continue going. So in this small part, you have the chloride reaching to the corrosion site and reacting with the chloride ions even more. In this case, that particular area will continue to grow while the other areas will start supporting the cathodic reactions. As a result, you have a pit-like structure formed, and this is the start of a pitting process. In this case, what happens is the Fe will react with the chloride to form ferrous chloride. This ferrous chloride will further react with water, that is, it will undergo hydrolysis to form HCl and FeOH twice. So the FeOH hydroxide will dissolve and leave with the Fe ions so that the pit is continued and you have additional HCl formed over here. So now even if you completely remove the electrolyte, you will still have the HCl ions present inside the pit. As a result, the pit will continue to grow in the absence of any external chloride. This is called autocatalysis. The pit growth is always autocatalytic. This is how a pit in carbon steel will be formed or under rust layers will be formed. So as given in this penultimate point. If in this case now we consider the stainless steel has this kind of uh, protective oxide film. Now, when this protective oxide film comes in contact with chloride, the chloride ions can penetrate through the oxide film because it is not compact. It is porous and it allows the chloride ions and moisture to go chloride ions to go inside. And stainless steel does not stain in normal water, but it does stain if you keep a stainless steel spoon in on a sea beach or in a box of salt, because the chloride ions are the ones which are able to penetrate this chloride film. Once it penetrates, the chloride ions can reach the steel surface, that is the Fe surface, and cause the same exact pitting mechanism for the pitting to grow. So if you look at the stainless steel sinks in your house, you will see that the pits form, once they are formed, they will continue to grow because the chloride because the chromium may not always be reformed after a certain point. This is actually related to the uh, active passive Evans diagram. So in Evans diagram, you have the active corrosion, then you have the passive film, and then you have the transpassive. So a stainless steel will have this kind of material. If you have the chloride ions and if they penetrate over here, the passive film will be resisted. However, if you keep on increasing the chloride medium or the chloride exposure, the cathodic branch will for chloride will increase, and finally it will intersect the transpassive region, which means that now from here you will not have any more oxide film. You will only have corrosion of the stainless steel happening. So that is how pitting corrosion will occur in stainless steel. The mechanism will be similar for aluminium or nickel alloys as well. So in this particular scenario, you will have chances of pitting not just in stainless steel but also in these kind of aluminum wall or flanges as well. Now this ASTM will typically give you the shape of the pits. So the pits can be conical, or they can be wide or shallow. Some pits will go deep, some pits will be shallow, but they will penetrate through the thickness. So just looking at from the surface, you will feel that the pit is really small, but actually it has expanded throughout the surface. This is especially dangerous because it can cause cracking in areas which we are not even aware of, and the cracks will be subsurface, so a bit difficult to detect and really dangerous. So this is how a pitting would look in an oil and gas or a scenario. Pitting in aluminum alloys happens because of course, the oxide film, but it also occurs because of the uh, intermetallics. So intermetallics are compounds such as aluminum, copper Fe, copper, magnesium, or MgCr, which occur during casting. So we really can't do much about these, and intermetallics by heat. They do not really change with respect to heat treatment. Fine intermetallics are zinc materials which are present along the grain boundaries. So these zinc fine intermetallics we can change using heat treatment. So when you have aluminium flanges or aluminium nuts and bolts, this is something that you will definitely experience in pitting. So you can see that the scale bar is just 10 microns, and the size here of the pit, if we see, it is hardly 2 microns. So you cannot detect this kind of pitting in aluminum alloys until the fixture will completely fall off. Hence the oil and gas industry really does need to look at the fixtures as well and see which alloy they are using for the fixtures or for the flanges, if at all they are using aluminium, to try to see what kind of pitting may definitely occur. In this case, the pitting occurs basically due to galvanic coupling again. So MgSi are anodic and aluminium is cathodic. So aluminium will remain and this MgSi will dissolve. So pit here will be formed something like this. In this case, in this first case, aluminium, copper are cathodic, and copper and Fe are cathodic, and aluminum is anodic. So the matrix is aluminium, and the intermetallic will not dissolve, but the surrounding matrix will dissolve. So you will have the pit something like this, where you have the intermetallic over here. Eventually, the pit will grow below the intermetallic and it will fall off. So you again have a complete pit form. Here it is dual way. So the Mg is anodic, and here the Mg will first dissolve. Then you only have aluminium and copper. So here now aluminium is anodic. So now the surrounding area matrix will dissolve and the copper will remain in the intermetallic. So such kind of behavior will be present depending on what the aluminum alloy used is, and that's why aluminum alloys are usually assumed to be just light in weight, and they are selected for their strength or their ductility, but it is quite necessary to look at their composition and check for the possible pitting mechanisms as well. The next type is crevice corrosion. Crevice corrosion is like a subtype of pitting corrosion. So you have pitting happening, but in this particular scenario, if now you put a washer, a crevice is formed between the stainless steel and the washer. Here the oxygen content is going to be low. As a result, the pitting is completely dependent on the HCl autocatalytic mechanism, and that's why it will continue. It will, even if you do not have oxygen, it will continue to grow. In fact, because it does not have oxygen, there is a possibility that it is ignored at the moment, but it is not actually seen, but it will eventually lead to material loss underneath the crevice corrosion, and the structure will lose its integrity. Filiform corrosion is a subtype of crevice corrosion. In this, the coating may appear not degraded if you just look at it, but underneath there may be material loss and growth of pits. For example, if you have a sample as given over here and you have a very thin coating, the issue is the coating is porous. So you may have an ingress of materials such as oxygen and moisture through the coating because it is a very thin coating, and they will interact with the underlying metal substrate. As a result, the coating will remain intact, but there will be corrosion occurring at the metal surface. As a result, on the surface the coating may look a bit protruded. That is called filiform corrosion. This is seen if the coating is really thin. So in oil and gas industry usually there won't be thin coatings, but if there is any sample or any component which has been pre-coated, there is a possibility of filiform corrosion occurring over there. The next type is intergranular corrosion. This is a really important type of corrosion for oil and gas industry. The reason is this corrosion occurs primarily in stainless steels, austenitic stainless steels, and it occurs in temperatures from 500 to 780 degrees Celsius, which are seen in many of the components in the industry. For this especially, it is important that the welds of the stainless steel components be looked at. The reason is when you have welds occurring, there will be a high temperature over here and a low temperature at further end, but this middle section would have the temperatures somewhere in this particular range. When you have temperatures in this particular range in this area, the carbides, there may be carbide formation. So let me just go into a bit of detail about this process. So stainless steel will usually have at least 11% chromium. Usually you will find that the chromium is 12% or above, or usually you'll see that it is at least 18%. So there is chromium oxide film all over the surface. Now when the stainless steel gets heated in this particular temperature range, the chromium from the grains moves towards the grain boundaries. As a result, the grain boundaries will have a reaction of the chromium and carbon to form chromium carbides. These chromium carbide precipitates will be present in the form of these black particles along the grain boundaries. This is called sensitization. Now the issue is this chromium has gone from just the area near the grain boundaries. So at the grain boundaries you have more than 18% chromium. In the grains also you have more than 11% chromium. However, in the small region next to the grain boundaries you will not have this. You will have very less chromium. That's why the chromium oxide film at these small region will not be intact or very good. As a result, in this, if you expose such a sensitized component to a chloride medium or even any other corrosive medium, the chloride will penetrate that poor chromium oxide film or no chromium oxide film and reach the metal underneath. As a result, the corrosion of the Fe in the stainless steel will start. This is called intergranular corrosion because it occurs in these areas between two grains. This is, as you can see, this is a very small section, so this is a bit difficult to detect visually unless you see a lot of corrosion products on the top. Hence, while monitoring, it is really important that the regions in these particular temperature ranges should be monitored. The carbides in this case act as the cathode and the depleted region as the side act as the anode. That is why the region here undergoes corrosion. The next component is exfoliation. Exfoliation corrosion is a special type of intergranular corrosion. So here it occurs mainly in aluminum and aluminum alloys. It does occur along the grain boundaries, but it is not because of sensitization. It is because the zinc particles or intermetallics, so the fine intermetallics are present along the grain boundaries. Hence, when you have a rolling direction in this way, the grains are elongated in the same direction. As a result, then when you expose this component to corrosive medium, such as moisture dissolved oxygen, chlorides, etc., they will react with the zinc intermetallics or the fine intermetallics along the grain boundaries and dissolve them. So basically you have layers of the grains separating from each other. This is especially dangerous if you have an aluminum flange or you have an aluminum valve, and if it undergoes such kind of exfoliation corrosion, you're basically going to uh, uh, get layers of the flange coming out entirely. That will lose its integrity and strength and cause a major leakage. So that is something that should be that is important to look at.